Hello, everyone. Today we are going to look at the proofs for three important formulas that we have for rigid bodies when we use the principle of moment and angular momentum. Okay, and um if you remember in the rigid body, I have shown you that first, instead of rigid body, we focus on a system of particles. So here, each one of these particles has its own mass. This location is the centroid of the system. This particle has mass mi, position vector r small I. It has velocity vi, and the force Fi is applied at that location. The centroid has the position vector rcm, and the position of the ith particle with respect to centroid is shown with capital R sub I. So we derive the equation for a system of particles, and then we say that for a rigid body we can generalize it by saying the mass of each one of these particles be infinitesimal dm, which in limit go to 0, and then the number of them will go to an infinite number of particles, so your summations that are now infinite summations will be replaced by integrals, but the equation that you derive will stay the same. If you remember back then, I showed you that sum of all moments with respect to the origin, which is summation over I of Ri cross Fi, equals to rate of change of total angular momentum of the system, which is summation of the individual angular momentums, and individual angular momentums are Ri cross Mvi. Okay, that's the definition. Position vector cross linear momentum is angular momentum. So this thing here I have proved to you in that video lecture, and I'm not going to redo it, but then I claim that not only I can write this moment rate of change of angular momentum with respect to the origin, I can also write that sum of the external moments with respect to the centroid is also equal to rate of change of total angular momentum of the system with respect to the centroid. Okay? So I claim that you can replace point O in this top equation here, this point O. You can now replace it with point Cm. But I never provided any proof why you can do that. So the first proof I want to do is this one. This is the number one proof. I want to show why you can also write this important equation about the centroid. Then we go to the two other proofs that are important. So first, let's see why this is happening, okay? Remember, just as an advice from me, never take anything just from instructor just because they are staying behind the lectern and giving you a presentation about this topic, okay? Because they are the PhD guys and you are not. No, always ask for a proof if you do not believe in it, if you do not like it or anything. At the least, the instructor would refer you to somewhere, a textbook or somewhere, to read about that proof if they don't have the time to prove it, okay? But do not just take everything without really convincing yourself that that is true. So the way I go about it is I relate this Ri vector that I have in these equations to the two other position vectors, cap Ri and Rcm. It's a simple addition of vectors here. You can say that Ri is equal to R about the centroid plus cap Ri. Correct? That's quite obvious. And now I'm going to replace that. So if I call this equation number 1 and I call this equation number 2, I'm going to plug 2 into 1. I'm going to plug 2, yeah, just one question mark should be enough. I'm going to plug 2 into 1 and see what happens. Okay, so what we do, we're going to plug 2 in 1. Let's see what happens if you do that. Then you will get what? On the left side, you will get summation over I of RCM cross Fi plus summation cap Ri cross Fi, correct? If you do the distribution of cross product with respect to addition, that's what you get on the left side. On the right side, what I can do is first I can simplify this or rewrite it basically, because you know when I take time derivative of this right hand side, let me talk about it right here. You know, this right hand side, when you take time derivative and exchange the position of time derivative and summation, this is going to be summation of time derivative of Ri, correct? Which is what? Which is Vi cross MV I, and then plus summation of Ri cross derivative of MVI. If M is constant, it is going to be MIAI, where A is the acceleration. And as you know, this term here, V cross MV, is 0 because the two vectors are parallel. So this term is what? It's 0. We know that, right? So if I want on the right hand side of this equation, I would replace this time derivative of summation Ri cross MVI, I replace it with the summation of Ri cross MIAI. Okay, I can do that one if I want to. And remember, that was equation number 1. So I replace it, then it is going to be summation over I of RCM cross MI and plus summation cap Ri cross MAI. Okay, so that's what you get so far. Now, let's see how we can do some simplification. So you know here in these two terms, RCM is a constant. It does not depend on the summation I. So I can bring it out and write it as RCM. Let's see if I can write it a little bit better. It's not really super easy to write on the monitor. Cross summation Fi. And this is going to be RCM cross summation of MIAI. Correct? And now, guess what? These two summations that you have in these two sides, they are the same thing, aren't they? Because for each particle, force applied to that particle is equal to its mass times its acceleration. Correct? So these terms that I underline in green, they are the same terms. And the RIs are the same, RCMs are the same term. So these two terms are exactly what? Equal Therefore, I can easily what? Cancel them from the two sides of this equation, right? So two of them are gone. That's good, right? The less the better, as we are looking into this nice formula in blue. So let's continue. By the way, let's see if I can bring this whole thing down a little bit. No. Want to write as clean as possible. There we go. And these red ones don't matter too much. You can easily clean them up. Good. Just want to draw a big line here, separate everything. So the problem statement is on the top and the proof is on the bottom. Good. Now, guess what you have on the bottom? This guy here, underlined in orange, that's clearly summation of the moments with respect to the centroid, isn't it? Sure. And this term on the right hand side, this guy, the same way that I showed you that summation of small r MIAI is what? RIMIVI, correct? They are the same thing. Can I rewrite this? Is there any way I can rewrite that one? Or you have to go through something? Well, let's see if we can go through any proof and show that that's the same as writing it as summation over I of RI cross, and for MAI or MIAI, I can write it as d over dt of MIVI. And note that here I'm just assuming a constant mass all the time. Okay, all the time I'm taking note that these are all for a constant mass system. Nothing is going to change here. So, good. And I told you this term on the right hand side is summation of the moments about the centroid. That's the definition of it. Good. Now, what is this term on the right hand side? So here I am doing the cross product of Ri times the angular momentum of these particles, okay? And first thing first is, can I take this dt out of that summation? If I can, then the remaining term, which is cap Ri cross MIVI, will be the definition of total angular momentum with respect to the centroid, right? Because all positions of the particles are now measured from this new origin, which is center of mass, with the position vectors cap Ri. So then it is going to be time derivative of summation of the moment with respect to the centroid. Can I do that? Can I bring this dt out? Right? And that's what we need to show. So my question is this: whether this guy is equal to time derivative of summation of Ri cross MIVI. Can I do that? Last time I showed you that if I take the derivative inside, I can do it, but it was with small Ri vector, not cap Ri. What about now? Okay, so here if I expand this time derivative, what do I get? Time goes inside the summation. You will get time derivative of Ri's. Okay, And what is time derivative of Ri? That's the important thing that we have to pay attention to. And of course, the second term is definitely this guy here. So it is going to be this term plus one additional term, which is time derivative of cap Ri cross Mi Vi, right? What can I do about that part? So here, let me first expand it. As I said, if you bring this dt inside, it is going to be summation of dri over dt cross mivi, and then plus that term we were looking into, which was summation of ri cross d over dt of mivi. So this term is clearly what I want. The only thing left to show is whether this term here is equal to 0. If this term is 0, then life is good. Now, last time I had small ri, time derivative of small ri was what? Was velocity of particle I with respect to what? With respect to origin. So this one was vi, if it was a small ri. And then vi and mvi were parallel, so the cross product was 0. But this time, this ri cap d over dt is what? What's the meaning of this? This is the rate of change of position vector of particle I with respect to the centroid. So this term is like velocity of particle I with respect to the centroid, isn't it? That's the definition of relative velocity. Okay? And now the question is, this VI with respect to the centroid means what? It means VI minus velocity of the centroid. That's the definition, relative velocity. So I can replace that with VI minus VCM. If VI sits here, clearly VI cross MVI is 0. The question is, what happens to this VCM? So first, let me expand this again. This is going to be summation over I of VI cross MVI minus summation of VCM cross MIVI. Where we know clearly this term is 0. What about this term? Well, here, VCM does not have anything to do with I. So I can bring the VCM out. And so I can write it like this. And what is this term? Summation of MIVI. What's that? Well, if you know, based on the definition of the centroid, this second term here is equal to what? Is equal to summation of the masses times velocity of the centroid. Let me write it properly. Correct? Because definition of velocity of the centroid is summation MIVI over summation MI, right? We know that definition, correct? Everybody knows that. Velocity of the centroid for a system of particles is summation MIVI divided by summation mi, the total mass of the system. Therefore, I can write it this way. And again, look here, this summation mi is just a constant number. VCM cross VCM is what? Again, 0. You see, so with some manipulations of the cross products and terms, I can show you really that finally this term on the right hand side can really be written only as what? As time derivative of. I can write it as time derivative of summation Ri cross Mi Vi, right? So this is what I wanted, to write it like this. And this is that term on the left. Now this term on the right, as you know, is clearly equal to what? d over dt of summation of moments, angular momentums about the centroid. So I can write it as h about the centroid. This is the total angular momentum of the centroid, of the system about the centroid. And now you see, sum of the moments about centroid is equal to e over dt of the total angular momentum about the centroid. So I can change the origin point and I can replace it with what? The centroid. But behind the scene, there is this much of proof going on to just show you that you can change the origin to the centroid and still use that equation. Okay, it's not that simple. That's proof number 1, which is very important because most of the time when we write this equation for the rigid bodies, we typically use the reference point to be the centroid of the rigid body. We barely use origin. Sometimes we might, but most of the time the reference point for this equation is centroid. Why is that equation true? I just showed you. Proof number 2, which we need to talk about, is now we have this equation that summation of the moments about centroid is equal to d over dt of h about the centroid. Correct? I just proved that to you. Now my new claim is this. I say h about the centroid can be written as I about the centroid times omega. Okay. And so if I plug it here, then I will get omega cross I omega plus I times alpha. And under specific conditions, the first term is 0, like 2D problems. So sum of the moment will simply be I times alpha. Because this I, in 3D problems, this I is not just a single number, it's just a matrix. It's a 3 by 3 matrix. Omega is a 3 by 1 vector. H is a 3 by 1 vector. Please look at the video I posted for 3D kinematics part 1. Okay, so in this case, I'm only going to show this, prove this in a 2D case for you. Why? And in 2D cases, if you plug it back, you can get to the simple equation that you always see. Sum of the moment about centroid equals I times alpha, right? Where alpha is the angular acceleration. Where does this one come from? How can I go from the original definition, which is summation of cap Ri cross Mi Vi? Look at this definition. How can I go from this summation to something nice like ICM times omega? Where do I rewrite my angular momentum in that nice format? Okay. So here we try to talk about that. If you remember the definition of HCM as we just saw it, the definition of HCM was, let me see, for some reason my pen is not cooperating well. So H about the centroid was, for a system of particles, summation of Ri cross what? Cross Mi Vi. Correct? Where again, what you had was, you had a system of particles, and let me copy this figure to the next page as well. It could be quite useful to have that right in front of our eyes here as well. So this is what we had, and here this Fi does not matter, so I'm going to get rid of it for you. So that was the definition of angular momentum of the whole system with respect to the centroid. Good. Now, how can I convert that to I times omega? Well, let's expand this and see what we get. How do I expand it? This time, I expand this velocity of the ith particle. I try to connect it to the velocity of what? The centroid. So this velocity of the ith particle, and if I have a separate velocity here for the centroid, like this, for example, how can I relate the velocity of 2 points on a rigid body? Now here, for the sake of proof, we have to make sure that point Mi and the centroid, they do belong to the same rigid body. They both rotate with angular velocity omega. If you don't assume that, then they are completely free to move from each other, then you cannot write it. So this is only for a rigid body, not just for any system of particles. They have to be connected as a rigid body. So I can relate Vi to VCM. Well, if you know from your rigid body kinematics, V of any point can be written as V of another point plus omega of that rigid body cross R of the left point with respect to the right point. Correct? That's the definition. This term here, R of I with respect to Cm, is a vector that connects your Cm to what? To the particle I, and that's the same as what? Cap Ri. Correct? Again, I emphasize one more time for you here that in this scenario, all of the system is a rigid body. The particles and the rigid body are constrained to move together. So here you have this vector omega. So again, this is the definition of cap Ri. Good? So from these two equations, what can I write if I call this one 1, if I call this one 2? From 1 and 2, what can I write? Can write that H about the centroid is equal to summation over I. And what's the difference here? You say, well, you just mentioned that it's a rigid body. If it's a rigid body, then I should not write a summation, right? Because how many of these particles do you have on the rigid body? Well, it depends on this mass Mi. If it's a finite mass, not infinitesimal, I only have so many of them. If this mass is an infinitesimal mass, then the summation will be converted to what? An integration. So here I write it as summation, but really for a rigid body, I will change this mass mi to an infinitesimal mass dm, and then the number of them will be infinite, so my summations will be converted into what? Into an integral. So here I just write it, but as I said, we have to do some modifications. So this is ri cross mvcm plus summation over I of Ri cross Mi omega cross Ri. True? That's the replacement. Now, what can we do? So, first question is, what is this term here on the left? Here, VCM is a constant term, correct? This VCM is a constant term. I can take it out of the cross product. So I can write this term here as summation MIRI cross VCM, and bring VCM out of the summation because it has nothing to do with I. What about the second term? In the second term, omega, there is an omega, there is Ri, and there is Ri. Okay? Now, I don't know if you know this important thing in cross product of the vectors, but what we have here is omega cross Ri and then crossing it back with Ri. So the result of that, if it's a 2D, if it's a simple 2D problem, just imagine for a moment, if it's a 2D problem, omega cross Ri, so here your omega is out of the plane, cross Ri is going to be perpendicular to Ri in the plane, correct? Probably in this direction. And then when you do Ri cross that, the result is going to be back in the direction of omega. Okay, so the result of that is whatever it is back in the direction of the omega. So I can write it as some single number times the direction of omega. Now, when it's 3D, you cannot write it as a number times omega. You have to write it as a matrix times vector omega. So here I'm showing it for the 2D case, but you can easily generalize it to the 3D case. So this whole thing from the theories you know from your vectors calculus, I can rewrite it in a nicer format, can't I? I can, right? So I can write this as summation of mi magnitude Ri squared times omega. Okay, this is A cross B cross A. We have to go and look it up, that what happens to A cross B cross A, right? Can I write it this way? Okay, I told you for a 2D case I can simply write it this way. For a 3D case it's not as simple, it's a matrix times that. But in 2D cases I can easily show you that this can be written that way. Now, what about here? Summation MIRI, what's the definition of that? Well, based on the definition of the centroid, position of the centroid in the past, if you remember, R of the centroid with respect to the origin was what? Was summation of MI, R of the particle i's with respect to the origin, divided by summation of mi's, correct? This was the definition of position vector of the centroid. Now here, instead of using position vectors of particle I with respect to the origin, I'm using the position vector of particle I with respect to the centroid. So what I'm doing here is, instead of point O, I'm replacing it with centroid. And I call this R of I with respect to the centroid, I call it what? Cap RI, of course. So clearly, this term on the top is equal to the total mass of the system times position vector of the centroid with respect to itself. And guess what? Position vector of any point with respect to itself is 0, so the whole thing is 0. So this whole thing is what? 0. You can easily see that from here. So this first term is entirely then 0, right? And so you're only down to the second term. And what is this guy? Now, as I said, when it's a rigid body, really what we have is an infinite number of particles where the masses of the particles are dm, an infinitesimal mass, and you have infinitely many of them. So what you really have in a rigid body, instead of this mi, you have what? You have dm and how many of these dm's do I have? Infinitely many. Okay, now I want to write nice, and again it is so slippery here. So then here this summation will be converted into integral of magnitude Ri squared dm. And guess what? What's the definition of this? That's exactly equal to mass moment of inertia with respect to the centroid. Done. Do you see? So in a 2D case, it is not such a hard thing to show that I can write my angular momentum of the system with respect to the centroid as mass moment of inertia with respect to the centroid times angular velocity. Okay, it's not such a big deal to show that. And here I've used this guy to prove that. So there we go. ICM times omega is equal to what? H about the centroid. As I said, in 2D cases, this is a single number. In 3D cases, it's not that simple. This is going to be in 3D cases. Let me write it for you. This term is going to be matrix I with respect to the centroid times vector omega. Okay, but as I said, the dimensions are important here. This guy is a 3 by 3 This guy is a 3 by 1. In 2D cases, they are both what? This is simply a 1 by 1, and this is a 1 by 1. So you can even remove it and write it as simply magnitude omega and magnitude h, because they are only about, let's say, if everything happening in xy plane, these h and omega are about z-axis. Okay, but you clearly see where you can prove this. The last proof I'm going to talk about today is, now sometimes, as I told you, in rigid body, my equations, this equation of moment and angular momentum is better be written with respect to a point that is not the centroid. So if I have this, as I told you, then in 2D cases, I can write it as summation of the moments about centroid is equal to, if I plug in ICM here times omega, and this ICM does not change with respect to time, then it is going to be ICM times alpha. And this is the equation that you use all the time when you solve 2D kinetics problems, right? This is one of your fundamental equations, one of the 3 important equations in 2D problems. Now, this is sometimes I prefer to use this equation, but instead of using my reference point to be the centroid, I want the reference point to be a point on the rigid body which is not the centroid. Also, it is not a fixed point. If there is any fixed point on the rigid body, you can easily show that this equation can be written about that fixed point as well. Okay, so if this is my rigid body, and if there is a fixed point on this rigid body, and you might call it point O, whether this O is origin or not, I can still say some of the moments about point O is equal to I about point O times what? Alpha. No problem. Okay, so you can write your moment equation about a fixed point on the rigid body, or you can write it about the centroid. No worries. The equation that I mentioned in the lecture for 2D problems kinetics for rigid body was, what if you want to write equations about an arbitrary point P, which is not the centroid, not a fixed point, and is not a point for which the acceleration is towards or away from the center of mass. So you cannot write this equation that simple. I mentioned that in such cases, the equation is going to be a little bit more involved, and the equation will be something like this, that sum of the moments about point P is going to be I about, not point P, about the centroid, times alpha minus, here you have one extra term, r of that point P with respect to the centroid cross mass of the rigid body times acceleration of the rigid body at the centroid. Okay? Yeah? So I told you you're gonna have one extra term if P is an arbitrary point on the rigid body that is not fixed. How can you show this thing? Why do we have an extra term here? That's one thing. And why in the first place you want to write your equations the moment you want to calculate some of the moments about point P? Well, one reason is there are some forces applied to point P and they are unknown forces. And by taking moments about this point where it has unknown reactions, unknown forces, you try to basically eliminate the moments of those unknown forces. You don't want those unknown forces to appear in your equation. You are trying to reduce the number of unknowns in this moment equation, right? In many times we try to choose an appropriate point for moments. If you remember from statics, we can say that some of the moments about any point on the plane or in the space for a rigid body in static equilibrium is equal to 0. Now, out of all these points that you can imagine, which points did your instructor suggest you to take moment about? If you remember, they were points where you have a lot of unknown reactions, correct? That's the same thing here. So at this point P, I have basically a bunch of what? I have a bunch of unknown reactions, and I'm trying to take moment about this this point P so that this left-hand side has as minimal as possible of the number of unknowns. Okay, so now that we know this has its own use, fine. Now, how can we prove this thing? Okay, so let's work on that. Okay, so here for a moment, let's get rid of this point O so it doesn't confuse you. This position vector P with respect to Cm that you see is this vector. Okay, this is R of P with respect to Cm. And you want to write your equations. So here, let's say the point that I can replace my resultant external forces on the rigid body can be designated as point A. So you know you can sum up all the external forces on the rigid body and call it what? Summation of the external forces, right? And then you can find a point on the rigid body where if you apply all of that resultant external force, sum of the external force, at point A, the moment of this single resultant force at point A with respect to the centroid is the same as the actual summation of the moment of all those external forces with respect to the centroid. So what you're doing is basically equivalent systems, right? What you learn in statics, equivalent systems. How much is your resultant force? Where does your resultant force pass from, correct? So here, assume that the resultant force, I show it with this summation Fe of external forces, and the equivalent system of forces should be acting at point A to create equivalent moments. Fine? Now, let's see what we can do. So here, we start with this equation that we had, and it was this guy, and we try to see if we can get to this point. So Let's start. Summation of the moments about the centroid. Let's focus on the left side. By the way, I call this equation number 1. And summation of the moments about centroid, what's the definition of it? It's the position vector from A with respect to Cm cross this summation of forces. So if I consider this position vector, which is r of A with respect to the centroid, this is going to be r of A with respect to the centroid cross this summation of the forces. That's the definition, right? That's about that. Now, this r of A with respect to Cm, I think I can write it as this r of P with respect to Cm, which is this vector, plus the r of A with respect to P, which is this vector. Correct? If I add these two vectors together, I should be easily able to recreate this vector. So I am going to write it as r of P with respect to Cm plus r of A with respect to P, the whole thing cross summation of the external forces. Now, let's see if we can do anything here. So, first of all, summation of the external forces, as you know it, is equal to what? Mass of the system times acceleration at the center of mass. So instead of this term, I can write it as total mass of the system times acceleration at the centroid, where again m is the mass of the total rigid body. Agreed? That's good. And now this whole thing should be equal to I about the centroid times alpha. Correct? Because sum of the moment about centroid is equal to I about centroid times alpha. That's the definition. Good. Now what happens here? So if I expand, I will get what? I will get r of A about P cross summation of external forces is equal to I Cm times alpha, and then this left term, which is r of P with respect to Cm cross external forces, I take it to the right hand side, it becomes negative. And you will get this. Now what? What's this term here? It is the position vector of A with respect to P cross the forces applied at A. Correct? So it's this force cross this arm. So it is going to be the moment of all these forces with respect to what? P. So it is this guy here on the left. Correct? So this term is clearly summation of the moments about point P. Good. And what was the summation of the external forces here? If you remember, that was m times ACM. So you will get your final equation. Then summation of the moments about point P is equal to I of Cm times alpha minus R of P with respect to Cm cross mass of the rigid body times acceleration at the center of mass. And this is exactly the equation we claimed in the beginning. Okay? And basically all that this one is what we call shifting moments. Okay? If you shift the moments that these forces are creating about point A, and we did it all with respect to Cm. Now, if you change your reference point from Cm to P, okay, then the moment of these forces with respect to P are not going to be the same as with respect to Cm. There is a difference between the moment that these forces create with respect to C and the moment these forces create with respect to P. What is that difference? The difference is the position vector between P and Cm cross this summation of the forces, which is basically this second term you will see here. Okay, so that is your third and last proof. I know probably this video was not what you were looking for most of the times. Say, I'm tired of proofs. That's okay. I didn't want to torture you, but I still want you to know that whenever anything happens in your class and anything is written on the board, if you don't like it and don't quite believe in it, please raise your hand, ask for a proof, whether the professor should prove it or refer you to somewhere in a textbook or somewhere else for a proof. Do not take anything just blindfolded, okay? Thank you so much. I'll see you in the next lecture.